Yeah, this is Derek in section 6.5, operations with roots. So in this one, we're going to add and subtract with roots and then multiply and divide with roots. For addition and subtraction, a couple of steps, we simplify all the radicals as much as we can. And then once we have them as simplified as possible, then we combine like terms. And like terms for radicals means everything except the numerical coefficient has to be the same. So in a couple of examples of like terms here would be 7 root 3 and then 2 root 3, because this is saying I have 7 root 3s and 2 root 3s, so those are the same thing. Likewise, this would be like 1x root 5 and then 9x root 5s, so all of that right there is the same. An example of not like terms would be 6 root 2 and 6 root 3. The 6's are the same, that doesn't matter. It's because the roots aren't the same. They're not this. We're not counting 6 of the same thing. Likewise here, this one has a y, that one has an x. So even though everything else is the same, these are not like terms because those variables are different. So for these first examples, we're looking at simplify if possible, otherwise enter the original expression. So this one says 6 root 2 minus root 2, and the minus root 2 there, it can really help to think of the invisible 1. You're going 6 of these minus 1 of these, and then if I say it to myself like that, it seems much clearer that I'm going to have 5 of those left. But the invisible one sometimes throws people. This one says 4 root 3 minus 2 root 5. Root 3s and root 5s are not the same thing, so I cannot subtract them. They're not the same size. So if that were the case, you would just enter the original expression. Okay, these next couple do have a bit of simplifying to do, so let me show you what these will look like. 2 root 27. So the way I usually write these is I look for the perfect square that's going to go in. So in this case, 9 times 3, so 9 is my square. And then I write that first, and I'll write the 3 second, because that 9 is what's going to come out. This 3 is what's going to stay behind. And if I'm adding and subtracting, I can kind of expect to get more 3s, because that's what's going to make this like terms. So here I would go plus 2, 147. Other than I have this little tip off that, hey, it might involve a 3. That's not the easiest number to spot, but if you go 3 into 147, you'll find it goes 49 times. So that's where it's nice to kind of go, I'm looking for 3s. And then this one, 3 goes in that, 25, so there's your perfect square. Whoops, and that's supposed to be a minus. So here we'll go 2 times 3 root 3, so square root of 9 made 3. This one's going to be 2 times 7 root 3, and then minus 5 root 3. And then just cleaning that up a little bit further, we got 6 root 3 plus 14 root 3 minus 5 root 3. So this would be 6 and 14 is 20, and then minus 5 would give us 15 root 3. This next one, same basic idea. Notice here a couple of them are like terms. They still need to be simplified, but while these are like terms, instead of simplifying 2 of them, I think I'm just going to go 10 square root 20x's minus 1 square root 20x would leave me 9 square root 20x's, and then minus root 45x. And then I just have to simplify 1 radical instead of 2. So here we'll go, this is going to be 9 and then 4 times 5x, which makes me kind of want to look for 5x's. And under here, this will be a 9 times a 5x as well. So bringing this one out, we would go 9 times 2, and then square root 5x minus 3, 5x. 9 times 2 would be 18, minus 3, and then we should have 15 square root 5x's. Okay, so for multiplication and division, we're going to pick up property 2 for radicals or roots. And this is much like property 1, but with a fraction. So property 1, we had square root of AB, could also be written A root B, if that was helpful. And this one is just the root of the fraction is the root of the numerator and denominator. So that's property 2. We'll use that with division. For multiplication, I just kind of set up this little thing to show how the pieces go together. The exact same way we would multiply polynomials. For instance, if we had 3x times 5x squared, we would do 3 times 5 and we would get 15, and x times x squared when we get x cubed. We multiply our coefficients together and we multiply our variables together. It's the exact same thing that happens with the roots. So we're doing a times c, the coefficients out front, and then the stuff under the root also multiplies. And it stays under the root unless it needs to be simplified. So let me start with this first one. I can write this a couple of ways. I can write this as 30 times 5 would be 150. And then I can note that 25 goes in there and I can simplify it a little bit. So 25 goes into 150 6 times and I get 5 root 6. A little bit slicker way to do that, I'll do right here, is to go, oh, 30, hey, that is 6 times 5 times this other 5 under there. So basically I'm using this property. And we got that 5 times 5, that's a 25, so that would bring out a 5 root 6. And I think I suffered a bit less just by spotting those 5s first than after the fact. This next one, we got 3c, square root 3c times square root 5c. So 3 times 5 will make a square root of 15. C times c would be c squared. But c squared, that's a perfect square, so we do have to simplify. So that will bring a c out front and root 15. This next example is a distribute. And so just the same as you would if we're working with just sort of integers and x's, variables, we're doing the exact same thing. We're just going to run the root 5 through those parentheses. So square root 5 times 2, remember that this has an invisible 1 in front, so it's really 2 times that 1. So we're just getting 2 root 5. And then here, 1 times the 3, that would be 3. Root 5 times root 5, you're welcome to just jump straight to 5 or even make that a 15. I'm going to show all my steps. So I'm going to write it as root 5 times root 5 is square root 25. If I'm doing this for me, I definitely would call that a 5. But again, this is just to kind of show people where that's coming from. So then we'll go 3 times 5, because square root of 25 is 5. And then 2 root 5 plus 15. This next one that looks like a FOIL is exactly that. It's just a FOIL. So we're going to go 3 times 1, and that will make 3. 3 times negative root 2, so 3 root 2 with a minus, and then those are both positive, so it'll be plus. 1 times root 2 would just be root 2. And root 2 times root 2, again, you're more than welcome to write 2. I'm going to write square root 4 for a second just to help people track. Minus 3 of these plus 1 of these would be minus 2 root 2's, and then minus the square root of 4 would be a 2 when I simplify. 3 minus 2 would leave 1, and then 2 root 2's. These are not like terms, same as over here, so I can't simplify that further. Okay, so for number 9, when I FOIL this, we're going to go 3 times 3, and that is 9. 3 times root g, that is 3 root g. And on the outside, we got minus 3 root g, and on the end, minus g squared. And then we just cancel. So we got plus 3 root g's, minus 3 root g's, so those drop out. And 9, and then this is minus square root g squared is just a g. Again, always welcome to just jump to the g. That's probably what I would actually do. In the next chapter, we'll see this is something called a difference of squares, and that there's a formula that we could apply there. Same thing for this one coming up, but for right now, I'm just going to show you that when we have this with that quantity squared, that means we have 2 of those. So we just write them side by side, and we'll just do our steps and we'll FOIL. So 5 times 5 will make 25. 5 times root 5 will make 5 root 5. On the inside, we're going to get another 5 root 5. And on the end, we're going to get plus square root 25. So this is going to go 25. We have 5 root 5s plus 5 more root 5s. That's going to be 10 root 5s all day. And square root of 25 will make a 5 there. And then finally, we got a couple of like terms. So 25 and 5 will make 30 plus 10 root 5. So then a couple of division problems. So here's one where we have 2 separate radicals. And there's a thing where we're not supposed to leave radicals in denominators. We have to do something called rationalize the denominator in that instance. And you'll see that next quarter. But in this case, if you look at this, if I write this as a single radical, like property 2 suggested I could, then this becomes that. And then I can go 2 goes into 98, and then that's 49 times. And b cubed, so I could cancel out a factor of b. And then all of a sudden this turns into something, once I simplify, that I can take the root of pretty easily. So square root of 49 becomes 7, and b squared would be b. This one, very similar. So this would be, if I think of those together, as 45w and 20w. So right there I can see the w's cancel. And then the 45 and the 20, I'm going to think of that 45 as a 5 times 9. I'm going to think of the 20 as a 5 times a 4. And that allows me to reduce out the 5s. And then square root of 9 is, and here we can think of this, we're basically doing that with it now. So square root of 9 makes 3, and square root of 4 makes 2. And you can also just think of it as a big old root of 9/4, which still makes 3/2.